Hello everyone, welcome to my video on trigonometric integration. So in order to solve trigonometric substitution problems, which we'll see in the next video, we first have to have a good understanding of trigonometric integration. So this is dealing with the integrals of multiples of sines and cos. So we'll start off with sines and cos. I'll show you later secants and tans and cotangents and cosecants. Okay, so before we begin, let me provide you with some trig properties or some trig identities that you learned before in secondary 5 that you'll need for this section. So here I'm providing you with trigonometric identities. So we begin with the reciprocal identities. Sine of x is equal to 1 over cosecant, cos is equal to 1 over secant, tan is equal to 1 over cotangent, so on and so forth. I have the quotient identities, so we know that tan is equal to sine over cos, cotangent is equal to cos over sine. And if you notice underneath the Pythagorean identities, there's sine squared plus cos squared equals 1, which is boxed in red. This one's super important. Make sure you have it memorized. Next, I provide you with the double angle formula. These have to be memorized. The half angle formulas as well. And here I provide you with the product formulas. Okay, so make sure these are memorized. Make sure you keep note of them because we're going to use them in solving these problems. So let's take a look at a strategy in order to solve trig integration problems. But in this specific case, we're dealing with sine times cos with different exponents. So if the integrals of the form sine to the m of x times cos to the n of x, okay, so they have different exponents. When we say sine to the m of x, think of it as sine of x, all that to the exponent m, okay? So this is just notation. We put the m in between the sine and the x, not to get confused with the fact that the m is not the exponent of the x, but it's in fact the exponent of the sine, okay? So if we have sine to the m of x times cos to the n of x, the strategy tells us to apply the following u substitution. So if n is odd, if the exponent of the cos is odd, what you do is you remove one cos. So we save a cos, we put him on the side, we save him, and we do the substitution. We let u equals sine of x. This is going to allow us to solve these types of problems. So just by looking at the exponents of sine and cos, we're able to solve it with the appropriate substitution. So if n is odd, u is sine of x. If m is odd, if the exponent of the sine is odd, we're going to save a sign, we're going to pull one of the signs out, and we're going to let u equal cos of x, okay? Why? Because think about the situation. If you let u equal cos of x and you take the derivative, well, that's negative sine. That's going to cancel out with one of the signs that we saved. Okay, we're going to see this with examples. So if the exponent of the sine is odd, we let u equal cos and we save a sign. The other case that we get is if they're both even. So if the exponent of m and n, the exponent of sine and cos are both even, then we have no choice. We have to apply the half angle formula. Okay, so recall half angle formula. I provided it in the formula sheets and the formula identities earlier, but it's sine squared. So whenever you have a sine squared, we can't integrate sine squared. We're going to have to rewrite it. How? By half angle. Rewriting it as 1 minus cos 2x divided by 2. And it's the same formula for cos of 2x. Cos squared of x, we cannot integrate it. We could only rewrite it in this form, which is essentially the exact same formula, but notice it's just, instead of a minus, it's a plus. So this switches to 1 plus cos 2x divided by 2. Okay, so let's go ahead and do some practice problems and apply our strategy. So in this example over here, we have to evaluate the integral of sine cubed of x dx. But wait, why are we allowed to integrate this type of function? Didn't I say earlier that the functions we're able to integrate are of the form sine times cos? Well, this is fine because we could think of this as, if I move the dx, we could think of this as sine cubed times cos to the 0 of x dx, right? Cos of x to the exponent 0 would just be 1, so it's like multiplying by 1. So we could think of it in this form, and now it satisfies our the form that we require. And what we do is we look at the exponents. The exponent of the cos is 0, which we can think as an even number. The exponent of the sine is a 3, which is odd. This is the one we care about. This is our strategy number 2. So if the exponent of sine is odd, what we do is we save a sign, and we do the u substitution, u equals cos. So let's give this a shot. We have the integral. I'm going to write it as sine squared x times sine of x dx. I'm not going to include the cos. I'm just going to write it in this form. So the 3 splits up to 2 times 1, right? So sine squared times sine, that's the same as sine cubed. So I'm not doing anything, I'm just saving a sign, I'm just pulling this one out. Okay. In the beginning you could do it in this form, but you don't have to. This is not obliged. This is just so that you could see the process. And what we're going to do now is let u equal cos of x. So if u is equal to cos, this seems unintuitive. Why are we letting u equal cos when our integral doesn't even have a cos involved? Well, now we have to think back to the introduction. One of the properties that I provided you with, I put it in a red box, was the Pythagorean theorem identity, was recall that sine squared of x plus cos squared of x, I put it in a red box because it's important, it's equal to 1. So we could rewrite sine squared, or we could isolate our sine squared, which is what we want over here, by moving the cos squared over on the other side. So this is equal to, so sine squared of x, if I subtract by cos squared, bring them on the other side, we get 1 minus cos squared. Okay. And now this makes sense. So using u equal cos of x, that means the derivative of cos is negative sine dx. So this integral becomes, let's do it in steps. Sine squared of x, I'm going to rewrite it as 1 minus cos squared of x times the sine of x that we pulled out dx, right? And now we know that cos is equal to u. So this part here, now we're going to transform everything in terms of u, is equal to the integral, that's an integral, of 1 minus cos squared would be really u squared. Okay. Sine of x, I can't do anything, I have to leave it. And dx, over here, we could solve for dx by dividing by negative sine of x. So by dividing over here, we could write this as du over negative sine x is equal to dx. So I'm going to substitute my dx with du over negative sine of x. And this is a good thing because, again, we're applying a u substitution. So it has to be expressed solely in terms of u. There can't be any x's. Well, this is a good thing because the signs cancel. But we still have the negative here that we have to worry about. So this negative here, I'm going to distribute it in, giving me the integral of u squared minus 1 du. Okay, so if you multiply this by a negative 1, the 1 becomes negative, I just put it in back, and the negative u squared becomes positive, which you wrote in the front over here. And now this is easy to integrate. The integral of u squared, let me do it down here, is u cubed over 3, and the integral of 1 is just minus u, okay, plus c. And now lastly, we have to come back in terms of x. We can't leave our answer in terms of u, but we know that u is equal to cos of x, so we could write this as cos cubed of x over 3 minus cos of x. I'm replacing my u's with cos, and then plus c. And this is the final answer. Okay. So keep in mind this property, very important, we're always going to be using it. Okay. Let's take a look at another example. So in the next example over here, it says to evaluate the integral sine to the 6x times cos to the 5x. So let's give this a shot. Pause the video, see if you're able to solve this on your own. So this is of the form sine times cos, so let's go ahead and apply our strategy. Looking at the exponent of the sine and looking at the exponent of the cos, our sine is even, the exponent is a 6, that's an even number. The exponent of the cos is a 5, that's an odd number. Since the exponent of the cos is odd, we're going to save a cos and let u equal sine. This is strategy number 1. Okay, so let me continue this in blue. So I'm going to write it as the integral of sine 6x times cos to the 4x. I'm saving my sine, my cos in this case. Okay, so I'm just removing one of the cos and rewriting cos to the 5x as cos to the 4 times cos to the 1. Okay, and now we're going to apply the u substitution, u equals sine. Okay, so the derivative of sine is cos, and solving for dx, we get du over cos of x. Okay, so that's our dx. So this can be rewritten as the integral, so this is side work. The sine to the 6 could be rewritten as u to the 6. We're substituting the sine with u. The cos to the 4x, there's nothing we could do with that. The cos of x has to stay. And the dx, we could rewrite it as du over cos. This is good because the coses cancel. Okay, great. But again, we're applying a u substitution. We have to express this solely in terms of u. We have an x, we have the cos to the 4x. How do we get rid of it? Again, it's the same property. It just looks different, but we're using the Pythagorean identity. We're using the fact that sine squared of x plus cos squared of x is equal to 1. Okay. But how do we get cos to the 4? Well, same idea. We bring the sine squared over, so we're left with cos squared is equal to 1 minus sine squared of x. And then cos squared, we're going to square the whole thing. Right? Cos squared, all that squared is really just cos to the 4. And we're going to square both sides of the equation. So we're going to substitute the cos to the 4 with 1 minus sine squared, all that squared, because that's equal to cos to the 4 du. But again, this is not written in terms of u, but this is better because our relationship between u and x is the fact that u is equal to sine of x. So this sine over here, I could rewrite it in terms of u. So instead of sine squared, we're going to write 1 minus u squared. And now this is expressed solely in terms of u. And this is easy to integrate. We just expand. So let me erase the bottom. So just to give myself some room, and let's go ahead and solve that. So let me expand this. We have u squared, 1 minus u squared squared. Think of it as 1 minus u squared times itself is simply just 1 minus 2u squared plus u to the 4. Okay. Du. And now at this stage, I'm going to distribute the u squared in the front to all the terms, giving me the integral of u squared minus 2u to the 4, and then u squared times u to the 6 is positive u to the, u squared times u to the 4, positive u to the 4 is positive u to the 6 du. And now we could integrate each term. So the first term, we add 1 to the exponent divided by that number, u cubed over 3. Same thing here, minus 2u5 over 5. And same thing here, add 1 to the exponent, divide by that number, plus u to the 7 over 7. Definite integral, so don't forget your plus c. And at the end, don't forget to come back in terms of x. So let's substitute with all our u's. We'll substitute the sine x, giving us sine x cubed, or sine cubed x, over 3 minus 2 sine to the 5x over 5 plus sine 7x over 7 plus c. And this is the final answer. Okay. Let's move on to the next example. So in the following example, we have to evaluate the integral from 0 to pi over 2 of cos squared x dx. So notice that the integral we're dealing with is a definite integral. The bounds of integration aren't defined. And the other thing we have to notice is that the exponent of the cos is even. So how do we deal with this? When the exponent of cos, so this again, we can think of it as cos squared times sine to the 0. So it's still of the form technically. And cos squared is even, so we're using a property 3, which tells us to use the half angle formula. So recall the half angle formula, cos squared x is going to be rewritten as 1 plus cos 2x over 2. So for cos, it's a plus. For sine squared, it would have been a minus over here. And this, we could also think of it as a half plus cos of 2x over 2. So I'm just dividing each term. Okay, I think it's easier to think of it in this form. But this is what we're going to do. We're going to rewrite this because we do not know how to integrate cos squared. We have to rewrite it in this form. So jumping over here, we have the integral from 0 to pi over 2. So instead of cos squared, I'm going to rewrite it using the half angle formula as a half plus cos 2x over 2 dx. Okay. And now what I'm going to do is I'm going to integrate each term individually. So we're going to integrate from 0 to pi over 2, the 1/2, and we're going to integrate the cos 2x over 2 from 0 to pi over 2. Okay, so we're going to do each term individually. The first term is easy, it's just a constant. So that gives us 1/2, and the integral of a constant is just x. And we have to apply FTC part 2, so we have to evaluate the upper bound and the lower bound, so from 0 to pi over 2. So this piece is done. Now we have to deal with this piece. How do we integrate this next part? The integral from 0 to pi over 2 of cos 2x. We could put the 1/2 in the front, the division of 2. You could think of it as a half in the front, so we're really just dealing with cos of 2x dx. How do we solve this one over here? Well, this is essentially just a u substitution. We could let u equal 2x. Take the derivative, it's 2 dx. So we could rewrite this as, let me continue here, 1/2 x 0 pi over 2. So I'm only applying the u substitution on the second piece, not the first piece. That's staying in terms of x, plus 1/2. It's a definite integral. We're applying a u substitution on a definite integral. You have to remember from the previous video, we changed our bounds of integration. Don't forget. So, let's put our integral sign. So the lower bound, 2 times 0 is 0, but pi over 2 times 2 is pi. So you have to change your bounds of integration. So we went from 0 to pi over 2 to 0 to pi because now we're integrating in terms of u. We're no longer integrating in terms of x. And this is cos of u. And dx, solving it for here, we divide it by 2, leaving us with du over 2 equals dx. So this is just du over 2, which we could put in the front as a quarter. So I'm going to go ahead and do that. A half times a half is a quarter. And this we know how to integrate. It's just the integral of cos, which we know. So the derivative of sine is cos, so the integral of cos is sine. So here, let's go ahead and evaluate. So we get a half pi over 2 minus 0. So we FTC part 2, put the upper bound subtracted by the lower bound. This is what we get. Plus a quarter. Integral of cos we said was sine. And we're evaluating it from 0 to pi. Okay. So notice that if you substitute the pi and the 0 into the sine of pi is 0, sine of 0 is 0. So this whole piece here on the right hand side is going to just cancel. You're just subtracting zeros. So this is 0. And here you have pi over 2 minus 0, which is pi over 2, times a half, which just gives us pi over 4. And this is the final answer. Okay, so remember, when you have a definite integral, you get an actual value. Whereas when you have an indefinite integral, if the bounds are not provided, you have to put your plus c. You get a function, or a class of functions, okay? So the answer here is pi over 4. Let's go ahead and take a look at the next example. So in the next example over here, set to evaluate the integral from 0 to pi over 3. So again, it's a definite integral of sine 2x times sine of x dx. So let's go ahead and solve these types of integrals. So the first thing you have to notice is that whatever's in the bracket, the argument of the sign, in this case, is different. How do we deal with this? So there's two ways. I'll show you both methods. The first way that I would personally do this, so method 1, is you could choose the method that you're comfortable with. When I see sine of 2x, right away I use the property that sine of 2x is equal to 2 sine of x cos of x. So this was a property that was provided to you at the beginning of the video. So this is the double angle formula for sine. So I'm rewriting sine 2x as this, okay? Just so that everyone has the same angle. So notice that here from 2x we reduce it down to x's. So everyone has the angle x. So this, using this property, the integral that we started with is equal to, so let me continue down here. the integral from 0 to pi over 3. Sine 2x, we're rewriting it as 2 sine squared x, because we have the sine that's here and the sine that's here. We multiply both of them, giving us sine squared, and times cos of x. Okay. So the 2 we could pull out because it's a constant. And now we're integrating from 0 to pi over 3, sine squared times cos. And now we look at the dx. We look at the exponents of the sine and the cos. The exponent of the sine is even, the exponent of the cos is odd. So since the exponent of the cos is odd, we'll let u equal sine. So this was property 1 in our strategy, the first one. So u equals sine, du equals cos dx. Solving for dx, we get du over cos is equal to dx. Okay, so we have the 2 sitting on the outside, 0 to pi over 3. Since we're applying a u substitution, the lower bound sine of 0 is 0. The upper bound, we're putting the pi over 3 in the sine, so sine of pi over 3, you have to remember your unit circle. It's root 3 over 2. Yeah. The sine squared becomes u squared. The cos stays, there's nothing we could do with that. And the dx, we're rewriting it as du over cos x, which is great because the cos x's cancel. Okay, so using our strategy, it allowed us to cancel out the cos's, and now we're left with just u's. So this is 2 integral 0 pi over, oh sorry, not pi over 3, root 3 over 2 of just u squared du. So we transformed it from something that was difficult to something that's easy to integrate. So this, using the power rule for integration. Okay, since we're integrating at this point, we remove the integral sign and the du. This is another thing I want to mention. Whenever you have an integral sign, you have to have a dx or a du that's written with it. The second you integrate, then you remove both of them together. So every time you have an integral sign, make sure you have a du or a dx or these two written together. Okay, so here u squared becomes u cubed over 3 from 0 to root 3 over 2. And this is equal to, let me take out the 2/3. And now we apply FDC part 2, giving us root 3 over 2, all this cubed, minus 0 cubed. Okay. So this cubed, what does that give us? That gives us 2/3. This is 0. This is times 3 root 3. And on the bottom we get 8, or 2 to the 3. The 3's cancel. One of the 2's cancel. So this is just root 3 over 4. And that's the final answer. Okay. So root 3 over 4. Let's go ahead and solve this using method 2 and see if we get the same answer, root 3 over 4. So the first method that I use only works because we have sine of 2x. The method that we're going to use now is stronger because it works when you have different angles. It doesn't necessarily have to be 2, it could be 3x, this could be 7x. It doesn't matter, as long as they're different. When the angles are different and you're multiplying sine times sine, you can use this following formula, which is sine of x times sine of y. So the arguments are different, is equal to 1/2, open bracket, cos of x minus y. So you subtract the angles, minus cos x plus y, you add the angles. Okay. Using this property, you could also solve this problem. So let's go ahead and do it. So jumping down here. So we have the integral from 0 to pi over 3. In this case, x is 2x and this y is x. So it transforms into 1/2, open bracket, cos of x minus y. So the first angle minus the second angle. So 2x minus x, which is just cos of x. And then minus cos of x plus y. So you add the angles, 2x plus x, which gives me cos of 3x. Okay. And you could solve this individually. So this is just 1/2 integral from 0 to pi over 3 cos of x dx, which we know how to do, minus 1/2. So this 1/2 distributes to both terms. So the minus from here comes here, the 1/2 distributes, so we have a half in front of this guy as well. from 0 to pi over 3 of cos of 3x dx. Okay, this one's easy to do. This one here requires a u substitution. Okay, so let's go ahead and integrate cos. The derivative of sine is cos, so the integral of cos is sine, giving us 1/2 sine of x. And we're applying FCC part 2. And here let's use the u substitution. U equals 3x. The derivative of u is 3 dx. Solving for x, for dx, you get dx equals d over 3. So we have minus 1/2. We're integrating. We have to change the bounds of integration. So this becomes 0. Pi over 3, we plug it into here. Pi over 3 times 3 in terms of u is just pi. And we're left with cos. Instead of 3x, we're substituting with u. So we're using this substitution. And dx, we're rewriting it as d over 3. Okay. The 3, I'm just going to remove it on the outside. So the division of 3, this becomes 1/6 in the front. And now we're integrating cos again. So we know the derivative of sine is cos. So the integral of cos is sine. So this is equal to 1/2 sine of pi over 3 minus sine of 0 minus 1/6, and the integral of of cos is sine. And we're going to do the upper bound minus the lower bound. I'm going to do it right away. Sine of pi is 0, sine of 0 is 0. All this cancels. So we're left with sine of 0, again this is 0. So we're left with sine of pi over 3 divided by 2. Sine of pi over 3 from our unit circle, we know it's root 3 over 2. And we have the 1/2 in the front. 1/2 times root 3 over 2 is root 3 over 4, which is the same answer that we got using method 1. Okay, so root 3 over 4 is the answer. So you can use whichever method you prefer. Okay. So let's go ahead and take a look at our final example. So in the next example over here, we have to evaluate the integral of sine squared x times cos squared x dx. So pause the video, give this a shot, see if you could solve the problem. This one over here is our case 3 in our strategy. Both cos and sine are even. Let's go ahead and use the half angle properties and switch their form. So this turns into the integral. Sine squared is going to be written as 1/2 minus cos 2x over 2. That's another way of writing sine squared. And the half angle formula for cos squared is 1/2, same thing, but a plus cos 2x over 2 dx. Okay. So you write it in this form. Next, what you do, well, one of the ways of doing it is distribute. So we're going to FOIL, it's a binomial times a binomial. So 1/2 times 1/2 is a quarter. 1/2 times cos 2x over 2 is cos 2x over 4. Then negative cos 2x over 2 times 1/2 is minus cos 2x over 4. Notice that they cancel, same number, opposite sign. And then lastly, we have negative cos 2x over 2 plus, multiplied by positive cos 2x over 2, which is minus cos squared of 2x over 4. All this dx. Okay, so these two terms cancel, which is great. That makes it easier. And what we're left with is the integral of 1/4 minus cos squared of 2x over 4. Okay. So dealing with the 1/4 is easy, that's just a constant. And dealing with the cos squared, we have some work to do. So what do we do here? We have the 1/4 dx minus 1/4 integral of cos squared of 2x dx. As I mentioned, cos squared, we can never integrate it. We don't know how to deal with cos squared, so what do we have to do? Apply half angle formula once again. Okay, so the integral of 1/4, I'm just going to do that right away. It's just x over 4. And this piece here, I'm going to write it as minus 1/4 integral of, instead of writing cos squared 2x, we're going to apply the half angle formula. So it's going to be 1/2 because it's cos, it's a plus. And notice that from here we took the x and we doubled it and divided by 2. Well, here in the angle we have 2x, so we're going to double it, which transforms it to 4x and then divided by 2. Okay, so we're doing the double angle formula. So we doubled the angle, but we reduced the power, which is important for us. Okay, so it's the same formula that we applied here. The only thing is instead of x going to 2x because it doubled, we went from 2x to 4x because the angle doubled. Okay, and now we could integrate the 1/2. That's easy. We could write it as x over 4. Maybe I'll deal with each term individually. Because we have a minus in the front, it distributes to both. So we have minus the integral of 1/8 dx minus the integral of 1/8 cos 4x dx. Okay. So we have x over 4 minus the integral of 1/8, which is just minus x over 8. And then lastly, we have minus 1/8, and we're integrating cos of 4x. So it's essentially a u substitution, like u equals 4x, du equals 4 dx. That means du over 4 equals dx. So we have the integral of cos u and dx over 4. This is equal to, let me just erase, give myself some room. X over 4 minus x over 8, you can multiply the top and bottom by 2, giving us 2x minus x, which is x over 8, right? A quarter is the same as 2/8. 2/8 minus 1/8 is 1/8. Minus 1 on 8 times 4 is 32. And we know that the integral of cos is sine. But instead of u, we're going to write what u is equal to, which is what I raised. It was a 4x. Okay. And since it's indefinite, the answer is plus c. So the final answer is x over 8 minus sine 4x over 32 plus c. And that's the final answer. Okay, so when the powers are even, you have to use the half angle. You have to use half angle or double angle formula, depends on how you think of it. You can think of it as half angle because 2x goes down to 1, or double depending if you go in the reverse order. Okay, so I hope this helped. I hope you have a better understanding of trig integration, and I'll see you in the next video.